I'm actually going to start with a video about atmospheric rivers. They say a picture says 1,000 words, so a short video says 1,000,000, maybe. So let's start with that, and then I'll get on to talking.
Imagine a river in the sky with more than twice the water of the Amazon. It's called an atmospheric river. Atmospheric rivers are long, narrow bands of concentrated water vapor that produce major amounts of rainfall. Atmospheric rivers begin in the warm waters of the Pacific, where water evaporates into the air. When this humid air meets a Pacific storm, the water vapor is concentrated and driven toward the coast, becoming a fire hose of rainfall and wind. Once the atmospheric river reaches the coastal mountains and the inland Sierra, the collision squeezes additional rain and snow from the system. Atmospheric rivers are responsible for up to half of California's annual precipitation. Scientists at Scripps Institution of Oceanography have developed a new system that rates atmospheric rivers on a scale from 1 to 5. The rating system helps identify atmospheric rivers that are beneficial, such as those that replenish reservoirs, and ones that produce hazards like flooding. Understanding atmospheric rivers is key to improving weather forecasts for better managing water resources and predicting flood risk.
As Harry said, I'll be talking more about atmospheric rivers and going into a lot more detail than that video. And I just want to acknowledge that I am presenting on behalf of the whole center. So there was a ton of work that I'm showing that are various different researchers throughout the center that have done. And in particular, I'd like to call out Deanna Nash, who helped quite a bit with this presentation. So atmospheric rivers, here's a satellite image of what we call precipitable water, so the water in the atmosphere. And the atmospheric rivers have specific characteristics. So one is a length and width. So the length, they're long and narrow. So the length is usually at least 2 times the width. And then there's components of it that is how we measure it. So the components are the transport or the winds and the water vapor. So this transport and winds, we often refer to atmospheric rivers or the measurement of atmospheric rivers as called integrated water vapor transport, or IVT. And that's a combination of the winds and the total amount of water in the atmosphere. I say the total amount of water in the atmosphere, but actually atmospheric rivers are generally much lower in the atmosphere. They're below generally speaking, the 10,000 feet and lower. So they come kind of relatively close to the surface of the earth. And atmospheric rivers are global phenomenon. So if you look at this map, all of these different red dots are indicating places where atmospheric rivers make landfall. So you can see they're all over the world. And the size of the dot is an indication of the average annual frequency that atmospheric rivers make landfall along the coast. And you can see our coastline along here stands out. They are generally subtropical, so if you look in the tropical range around the equator from 20 north to 20 south, there's less of them, and they extend farther into the subtropics and the polar regions. One question I had is, how come I've just started hearing about atmospheric rivers? And as this map suggests in some of the videos, they're a natural phenomenon. They've always existed, but the term hadn't been coined really in the scientific literature until 1997, 1999, depending who you ask. And there's other features in the atmosphere that are similar related to atmospheric rivers. And so the scientific community went back and forth on kind of what to call them and how to define them. And it's been really recently, within the last 10 years, that the term has been, I would say, more broadly accepted within the scientific community. And then there's been more additional outreach to media, broadcast mets, to talk about this storm type. And some of you may have heard the word Pineapple Express. So Pineapple Express is actually a type of atmospheric river. So the name came from, because it's atmospheric river that generally comes, actually I'll go back a couple slides. It's like this one, where it generally comes from Hawaii, and that orientation to California is relatively impactful for our state. And so that's where the term Pineapple Express came from, was this type of atmospheric river that started in the region of Hawaii. Then I think there's a sharp seasonality to atmospheric rivers. And so if you look here, there's a map along the US West Coast, and this is Southern California, Northern California, going along to Oregon, Washington, British Columbia, Southeast Alaska, and Southwest Alaska. And as you can see, if we're gonna start kind of in the spring, summer, in Alaska, and then it comes down along the coast. And so that seasonality doesn't mean that we don't get atmospheric rivers any other time of the year, but that's really where we get the biggest atmospheric rivers, and they're most impactful and the most frequent atmospheric rivers. The next one is, this is important for thinking about what the video was talking about in terms of the skill or atmospheric rivers in improving water management or emergency management. So what this graphic is showing is the predictability of atmospheric rivers relative to precipitation using that term I said before, IVT, the integrated water vapor transport, so the combination of the winds and the water vapor. And if you look, this is the forecast day. And so this is 24 hours ahead, 48 hours, 72, and you could go up. And the improved forecast skill goes up. So the higher the number, the better the forecast skill. And as you expect, at day one, you have a great forecast skill. And then as you go out in time, the forecast skill drops off. And this black line is looking at IVT and atmospheric rivers, whereas this gray line is looking at precipitation. And so there's actually more skill in looking at forecast of atmospheric rivers. And so this is especially noticeable at what we consider some of the longer lead times in the weather forecasting, kind of five to 7 days, where there's this indication that there's going to be potentially a storm coming. The shift in where exactly it may make landfall and how much precipitation is kind of rained out of that atmospheric river may vary a bit, but it's a good situational awareness to know that there's something might be coming towards you and impacting your region. And so this is just another way of showing the same result. And so this is by year, starting in 1984, and this is for day 7, so a week out, what the forecast would be. And you can see the skill, similarly, the improved forecast skill goes up, and the black line is IVT, or atmospheric rivers, and it's always higher than precipitation. And so we use this in a lot of what we talk about in terms of forecast skill and forecast awareness, providing forecast for atmospheric rivers, which I'll talk about a little bit later on. So many of you know this. You live in San Diego, I assume. But our precipitation, so rainfall here, we don't get snowfall, but when I say precipitation, I mean both rainfall and snowfall, is highly variable, right? It goes up and down. 2 years ago it was pretty dry. Last year was pretty wet. This year was relatively wet. So we have this high variability. And we've actually looked at this, and this really jumps out. So this is a map, obviously, of the US. And if you look, California really jumps out. And then Southern California, even more so than the rest of California. And what each of these dots represent is a weather station that measures precipitation. And the coloring of the dot represents what we call the coefficient of variation. So it's how much it varies from year to year. And so if you look here, in Southern California, when it's this 4 to 5, our precipitation, about half of it can vary from year to year. So that's pretty extreme. And this is something, California is relatively unique in terms of that variability. So not knowing year to year how much rain we're going to get or how much precipitation we're going to get can be, as you can imagine, a water management challenge. For emergency management, it could be another challenge. And so this is one of the things at the center we've been really focusing on, is how do we improve those forecasts of atmospheric rivers at all sorts of different timescales to help with that awareness. I think this is a pretty cool figure. This is something that it's showing the number of days to generally get that it takes to get half the precipitation. And so if you look here, again, California stands out a little less so. Some of the monsoons areas stand out as well. But in general, it's about 5 to 10 days throughout much of California, 10 to 15 in the northern parts where it's wetter, to get about half the precipitation. So it doesn't take much. And what that means is it's generally the really big storms that matter a lot for whether or not it's going to be a dry or wet year. And if we look at what most of those storms are, they're atmospheric rivers. And so what this is showing is this is the percent contribution of atmospheric rivers to total annual average precipitation. And if you look along this kind of Russian River area or Northern California, it's kind of the bullseye where it's upwards of 50%. Down here, it's close to 40 to 50%, and as you move inland, that starts to decrease. So as the atmospheric river comes across the ocean, like the video showed, and intersects with our topography, we start to see a lot of precipitation. And so those atmospheric rivers are really important. The flip side of that, as indicated, they can also be relatively impactful. And so this is just showing the post-fire debris flow in Montecito in 2018, which was caused, it was on the back end of an atmospheric river, something called a narrow cold frontal rain band, where you have really intense precipitation, not necessarily long periods of time, which can lead to these post-fire debris flows. And then this was a study done by a colleague that looked at the damages from flood insurance throughout the West, and this is the percentage or fraction of damages that were due to atmospheric rivers. And as you can see in California, upwards of almost 90% in most places, and overall throughout the Western US, it was about 84% of flood damages were caused by atmospheric rivers. So, and the reason why atmospheric rivers are so impactful, right? And again, this is something that the video showed, but you see these atmospheric rivers that they come across the ocean, and the wind, right, is a combination of that moisture and the wind, and then when it intersects with our topography and our mountains, it goes up and produces the precipitation. And then this is the idea of the rain shadow on the desert on the other side. So it doesn't necessarily always make it over to the mountains, and then that's where you get the deserts. And so this is, if you think about, so one thing that's really cool about San Diego is in terms of, from coast to mountain to desert, we're one of the most biodiverse counties, in part because of our topography and how the precipitation comes in along the coast and the mountains, and then we get all the way to the deserts. And so this feature here that happens along our coast and with the Sierras and inland, it also happens here more specifically in San Diego too. And so this is looking at that atmospheric river scale that was mentioned. It's similar to the idea of a hurricane scale, but there are some differences I will cover. And it goes from an AR, which is atmospheric river 1, all the way through an AR 5. And generally what we think about is atmospheric rivers 1 and 2 are relatively beneficial. Atmospheric river 3 can be potentially beneficial or hazardous. And then atmospheric rivers 4 and 5 are generally more hazardous conditions. And so this is based on 2 different criteria. One is the maximum strength of the atmospheric river, which you see here. This is, again, this IVT. What I mentioned is that combination of the winds and the precipitation. And then the other one is the duration, right? If you have something that comes through relatively quickly, it's generally not as impactful as something that lingers and stays for a long time. And so you can get various different combinations depending on, if it lasted for about 2 days and was moderate, it could be somewhere between this AR2 or AR3 if it was 2 to 3 days. And so that's how you can look at the scale, is thinking about it. One thing that's really unique about the atmospheric river scale, and is different than, say, the hurricane scale, is it's location dependent. And so this was from a forecast this year, and this is a map, and each one of these dots represent the AR scale at that specific location, right? And so if you're looking at this map, what you see along Oregon, most of it was an AR3, but if you come down into California, it was an AR1, and then other parts, Southern California didn't have any impact, so it wasn't an AR, and that's why you're seeing the white dots. And the reason for this is if you think about it, right, the atmospheric river in these areas where it's an AR3 are most likely to be more impactful and potentially more hazardous because it's both stronger and or longer in duration. Whereas if you go farther south where it's shorter and not as strong, those impacts aren't likely to be as strong. And so that's one thing I think that at times can confuse people, because you're used to thinking like a hurricane has a number associated with it, where the atmospheric river scale for your location it does, but it can change depending on your location. And there was a study that was done that actually looked at the atmospheric river scale and with the National Weather Service warning watches and advisories. And so one of the things you're seeing here is the correlation between the atmospheric river scale and when these warning watches or advisories were issued. And there's relatively strong correlation throughout much of the West between the scale and these advisories. So this just links even more so the importance of the atmospheric rivers and the scale to these potential impacts. The other thing that we looked at was the flood insurance cost by scale. And so what you can see here is that it actually scales, the flood insurance cost scale by AR scale as well. And one of the things, as you can see, some of these are looking at the outliers here. Sometimes you can have an AR1 that is really impactful Oftentimes what's associated with that is that that's an atmospheric river one that comes on the back of a sequence of atmospheric rivers. And so it's when the reservoirs are already full, soils are already saturated, those sorts of conditions which are more likely to lead to flood damages than an AR1 in November when the soils are still dry, for example. So what about atmospheric rivers in the future? So this is, I think, a nice summary, and I'll dig into it a little bit more about what do we know about atmospheric rivers in the future. The frequency is likely to increase. In terms of flooding, in part because atmospheric rivers are generally warmer storms. They're bringing in kind of warm tropical water over, and so it can actually lead to more snow melt. And so rain on snow is something you might have heard of, and so that can potentially lead to more melt. Also, in generally just warmer temperatures, there's more snow and ice melt. Atmospheric rivers, the other thing that we know is, just in general with global warming, the atmosphere can hold more moisture. And so if the atmospheric river has more moisture in it, there's more moisture for it to potentially rain out. And so this is one of the reasons that atmospheric rivers are projected to become stronger in the future, is that the ability to hold more moisture. There's definitely still some uncertainty in the projections going forward, and then the more extreme precipitation, because of the ability to hold more water, and then can also then lead to more flooding. And so this is kind of the overall summary of atmospheric rivers and linking to future impacts. And so if we look here now, this is a study that was using the last set of global climate models. We call it CMIP5, and this is using a more kind of the business as normal, or a more a higher level of greenhouse gases in the atmosphere. For those that are familiar, it's called RCP 8.5, and it's comparing a future period at the end of the century compared to a historical period. And so what this is showing is the percent change in how much more atmospheric rivers contribute to precipitation. And so similar to before, along the coast, we see higher percentages, around 20% to 25%. And as you move inland, that starts to decrease a little bit. But what this is showing is that atmospheric rivers are going to become increasingly important to our overall precipitation regime. The other part of it is looking at extremes. And so this is just a case looking at the Russian River. And this is the daily precipitation percentile. So greater than 99th percentile are the really, really big events. 50 to 60 is kind of the median, middle of the road events. And then the gray here is looking at atmospheric river precipitation, and the white is non-atmospheric river precipitation. And so what really stands out, probably to all of us, is this, these extreme events, and most of these are going to be caused by atmospheric river precipitation, and they're becoming significantly more extreme, especially the most extreme. And so this is some of the things that the projections are indicating, that the most extreme atmospheric rivers have the potential to become a lot more extreme. And again, this has to do with the ability for the atmospheric rivers to hold more moisture. The wind component of atmospheric rivers is a lot more variable in the climate models, and it's not really clear how much that wind component will actually impact it. It has to do more with that thermodynamic feature of being able to hold more moisture in the atmosphere. That being said, there's always caveats to this, right? There's always some more to learn. And so there was a modeling study done by some people in our group that looked at the 2017 atmospheric river that was part of the Oroville Dam, where the spillway collapsed. And so that atmospheric river, it was one, but it had two separate pulses. So the orientation of it slightly changed. And so this is looking at pulse 1. And this is looking at pulse 2. And this is on the Feather River Basin, which is one of the major basins that feeds into Oroville Dam. And what you're looking at, this color bar, is the difference in precipitation. And so this is actually the present day versus pre-industrial model simulation. And you can see that there's slight differences, right? 11% change versus 15%. But if you look at, the near future, which was about 2050, and the future between these two pulses is actually quite significant in terms of how much, through this modeling showing, can be attributed to climate change, or how much change could be attributed to climate change. This was only 9%, whereas this one's 26%. That's a pretty big difference. Similarly here, 21 to 59%. And our understanding of it is based on the modeling study. This has a lot to do with the orientation of the atmospheric river and how that moisture is transported and intersects with the topography. Even on smaller scales, it can be really important. And based on that, the more precipitation rains out. And so one of the things that we are now looking into is, and I'll talk about this a little bit more, but last winter when we had that series of 9 atmospheric rivers, we called it an atmospheric river family, the scientists that led this study is looking at that one because each one of those atmospheric rivers were so unique to understand and do a similar study and see how much that orientation really impacted it for different places throughout the state and different topography. So there's a continuation of the study, but it's an indication that, it's not all the same for all atmospheric rivers. It can vary quite a bit in terms of how climate change affects it. So now I'm going to shift gears a little bit and talk about how we study atmospheric rivers and why we do it and some of the improvements we're working on towards improving forecast. And so we really take a multi-pronged approach at the center where we combine all these different components of it. So one is observations, and I'll touch on that, but we have a pretty robust field team that collects observations. Another thing I'll touch on, which is called atmospheric river reconnaissance, where we collect data in the atmospheric rivers themselves. That can be used in modeling, because modeling, what we need is to know and understand what the conditions are before the model starts, which is called initial conditions, so to improve the modeling. And then also having that data, those observations, is how we know how well the model's doing. Without a ground truth or observation, there's no way to know if the model is good or bad. And so that's one way that we use to verify the model is through those observations. And then again, this is a large modeling effort, and I will touch on that too, but we have, we actually with San Diego Supercomputer have an agreement, and they had an older supercomputer that we were able to use and develop modeling studies and actually do what we call near real-time forecast of atmospheric rivers, which I'll touch on a little bit more too. And then this other part is the research and verification, right? So understanding what are the important features that make sure we get right in understanding the atmospheric rivers. And then in looking at those forecasts, where were they right? Where were they wrong? Why was this storm right? Why was the forecast for the storm better and this one worse? And so understanding some of those components to better understand how the models capture the atmospheric river to then improve the models and improve the forecast. So I will actually I will talk a lot more about last winter because we've had a chance to really look at that data and deep dive in. But this is something that actually just came out today. A colleague worked on this. We call it the AR landfall map. And this is looking at the water year. So we think of things in the water year, which starts in October and then goes all the way to September 30th. And the idea is that we capture kind of the precipitation that comes down. And so if you think about it, fall, November, we start to get some of that precipitation. December, January, and February, and March are kind of the big months. And then any spring precipitation, which lingers. And every now and then we'll get a summer storm, right? And so we capture that full cycle. So we call it the water year from October to September. And so this is, given that this is kind of the end of our big month, this is looking at the atmospheric rivers that have made landfall thus far this year. So there's actually been 51 of them. And one thing, it's a little hard to see, and I will fully acknowledge that, but if you look at the dates for California, besides this December one, many of these dates are late in January or February and March. And so I don't know if you guys kind of internally realize, I have to admit, I think about a lot more, but it was a pretty slow start to the water year in terms of precipitation. By December timeframe, it was still pretty dry around, and we hadn't had that much rain. There wasn't a lot of snow in the Sierras. We go up to Big Bear a lot. There wasn't a lot of snow up there, so there wasn't a lot that was around. And then, we had that big January 22nd event here in San Diego, and then LA had one a couple weeks later. And then we started to get more of the springtime, like late February and springtime precipitation. So this was a later start. And you can actually see, if you could squint your eyes and see some of these dates, most of these dates are February and March. And so this really shows that the importance of atmospheric rivers in determining whether it's going to be a wet or dry year. So what I actually will focus a lot more on is this family of atmospheric rivers that happened last year, starting December 27th, that went through January 16th, 17th, depending on what we sometimes work in UTC versus Pacific time. But and so there were 9 atmospheric rivers. There was one that it was actually the strongest one that was hit a little bit farther north. So I don't think we were quite as aware, but that was exceptional in strength. But what was interesting about this was how strong and how frequent and how many they were all at once. And we did a deep dive on this family of atmospheric rivers that's in a story map. And so here's the ArcGIS story code or QR code if you want to look into it a little bit more. I can also share the website as well. But I'll be talking about these and how we study them using this family of 9 ARs as an example. So one of the things that the center does work a lot with is use the information that we have about atmospheric rivers and produces forecast products on our website. So if you go to cw3.ucsd.edu, there's a whole bunch of atmospheric river forecast products. I will say right now it's not that interesting. We're kind of at the end of the atmospheric river season. So, next November, if you're interested, it's a great place to go. But this is one of, I think, the most informative and one of the forecast images that we get the most people using or interested in because of the foresight it provides. And so what this is showing is it uses various different models to show the probability of atmospheric river conditions along the U.S. West Coast. And so what you see here is the darker purple colors are higher probability of atmospheric river conditions. And this is based on lead time. So this is today all the way out to 16 days. And this was from Wednesday, December 28th. So right after that first atmospheric river and right before that series started. And you can see that it wasn't certain and not everything's exactly where they made landfall, but this indication of this long sequence of atmospheric rivers over the next 16 days. And so there was we work pretty closely with the California Department of Water Resources. And so this was an indication of there's something coming and we got to be alert and aware. And so this is actually a map of looking at the storm reports during this family of 9 atmospheric rivers. And you can see the different types of reports just to show how impactful it is. So the green is the hydrologic, winter weather, wind-related, or debris flows. And so at each day, you can see those storm reports. And this image here, this GIF here, it's going by date. Let's see if I can get it to restart. There it goes. And you can see where those storm reports were, and so where the largest impact was in terms of the atmospheric rivers. So how do we study these, and what did we do last winter to help study these? One of the big things that has been initiated at the center is atmospheric river reconnaissance, or AR Recon. It's the same idea as what you hear about the hurricane hunters, or when they go through hurricanes to drop what we call dropsondes, and they go through the atmospheric river and they collect temperature, precipitation, wind, and humidity data. And so they go through and they get this information. One question we often get asked, so what about satellites? Because satellites, you can generally kind of see an atmospheric river, but because of the cloudiness and because atmospheric rivers are so low in the atmosphere, a lot of that information is lost or it can't be used because of the cloudiness. And one of the studies we did actually showed that by having the dropsonde data, more of the satellite data was actually assimilated or used in the models because it had something to verify that it was good data. In addition to this dropsonde data, we also have, it's a new, relatively new technology that's called radio occultation, which goes outward from the plane instead of downward. So getting outward and downward. And then also working with Luca Centrioni here at Scripps, there's these drifting buoys that we add pressure sensors to. And those pressure sensors provide information about what's going on in the surface of the ocean. So this is just a look at all the different flights that went out during last year. And I should have noted this is a collaboration between the U.S. Air Force and NOAA. And so there's 2 different federal agencies that do the flights and the dropsondes. And then here's where all the different drifting buoys are out in the Pacific. And the one that I forgot to mention was on land. So the dropsondes go down but once the atmospheric river comes on land, we release radiosondes or weather balloons, and those go up. And so this helps with the evolution of the atmospheric river that was on land to see how it evolves on land and how it changes on land. This is then a process. So all this information and all these different observations, they go in they call through what's called the GTS, or it's a location which gathers a whole bunch of information and observations that can then be assimilated or used by the models. And so those get put into the weather models, and that provides what we call the initial conditions, or the conditions that the model knows what's going on at that moment in time before it's starting. And so the ocean generally is a bit of a desert in terms of observations, especially in those lower atmosphere, kind of where the satellites don't necessarily always reach. And so the dropsondes provide that information of what's going on at that state of time before the models kick off. And then the data assimilation goes into the weather models, and that's when you get your forecast. And this is for all of last water year, so not just the family of 9 ARs, but there's studies that do, so it integrates the information for atmospheric river reconnaissance, so those dropsonde informations, and then without. And so this is looking at the forecast improvement for different locations with those with the dropsondes from atmospheric reconnaissance and without. And so what you're seeing here, this is a West Coast, this is southern Canada, I think. But what I want to bring your attention to really is here, this is California. And these different color bars are the amount of precipitation and the improvement. So the blue is 1/10 of an inch, red's 1/2 an inch, 1 inch, and 2.5 inches. And what you see is last winter, on the days with substantial precipitation for California, we saw almost a 12% increase by including the dropsondes in the weather models, by assimilating that information, which is huge. That sort of improvement in that short of period of time, you generally think of is about 8 years. And so this is how valuable that information is in improving those forecasts for California. The other thing, and I mentioned this a little bit earlier, we have a regional weather model. So it takes the global models that NOAA produces, or in other places, ECMWF in Europe, and it takes those, and then at the outside, it uses that information on the outside of this 9-kilometer domain here to start the weather model, and then it downscales it and produces a weather model at smaller and smaller scales. So it's able to capture more features, especially with our topography. The other thing we're able to do is run what we call an ensemble. So a very large, we run the model many times to try and get a sense of the probability of likelihood of something happening. And so it's called a probabilistic prediction. And so this is just one example. This was from this year, actually. And so each one of these little lines represents one model run, and the different colors here is, the different precipitation at different times. But it gives you then this probability of, for here, it's about a 5% probability of 2 to 3 inches on January 23rd and 24th. And so this helps I would say the weather, like we always know, I would say generally speaking, when it says it's going to rain, a 1/4 of an inch today, the likelihood of it actually being a 1/4 of an inch, exactly, is pretty low. And that's what we call the deterministic model. It's one value and it has one number. The Weather Service and weather prediction is moving to more this probabilistic framework of providing more information about what's the probability of having this threshold of precipitation. And so the idea behind that is there's a lot of experts out there on how to manage their specific water or their specific watershed. So it's providing more information and more context for them to use to make that decision of what to do and how to manage that water. And building on this, so we run this model this is looking at the US national model, and this is looking at the European model. And this was for the first atmospheric river, or I think it was the second atmospheric river during that family of 9 8Rs, and had a really big impact in San Francisco. And so this is looking at a grid point in San Francisco. And the red here is what was actually observed. The black is the maximum that came out of this ensemble. It's many runs from the US national model on the top and the European national model at the bottom. But because we run a regional model that we can run many times building on what's already been done, what you see is the CW3 ensemble was actually able to capture this extreme, right? This fell within the range of the ensemble. So this shows that the ensemble showed that there's at least a probability of something that extreme happening, where the other models kind of missed it. And so this is the ability, when you have the computing and you're focused regionally, you're able to actually work on some of this. So the other thing that I feel like this is all the craze now, but the other thing that we've been looking at in this probabilistic phase is machine learning. And so this is another way of looking at kind of the probabilistic skill, and this is for 1 inch of precipitation, and the forecast improvement went up. Like as the numbers get bigger, that's an indication of forecast improvement. The blue line is a US national model. The green line is a European model. And so here it's showing that the green line did a better job of capturing the probability of 1 inch precipitation or more during that family of 9 ARs. Oh, my animation didn't work. Bummer. Well, under this white box, if you can imagine it with your eyes, there's a red line here, which shows that the West Wharf ensemble did a little bit better. But then what we're actually seeing is with machine learning, it bumps it up a little bit more. And so after the ensemble is produced, there's a machine learning that kind of takes out biases or other things that can improve it even more. And so this is something we're starting to see a lot more in the weather forecasting industry is after the modeling's been completed, using machine learning to take out biases or other things that they know the model doesn't capture quite as well to actually improve the model. Sorry about that. I thought that was going to work. The other thing I touched on, I'm not going to go into a lot of detail here, and I realize the slide's super busy, but that we have a ton of observations throughout the state of California, and now we're starting to expand into Colorado and also into the Pacific Northwest. And so we measure a whole bunch of different things. So this is one kind of this is actually at an elementary school. We partnered with an elementary school to install a weather station there. It met the research needs, but now there's also the ability for the students to go out to it, look at the data. We've done a weather balloon launch there. And so there's temperature, there's pressure, wind, hourly precipitation, soil moisture at different levels, and soil temperature. And so we have stations throughout the state that measure all these. This one is called a freezing level radar. And so what these black dots show is when the precipitation changes from rain to snow at what height, which you can imagine for some storms is super important. You know, if it all falls as snow, the likelihood of flooding is a lot less versus if it all falls on rain. This is something that we saw during those family of 9 atmospheric rivers last year. And this is looking at the precipitation phase, and so if it's more of a drizzle, if they're bigger drops and types, because that can also impact it as well. The last thing I'm going to touch on is, so what do we do with all these better forecasts? And one of the things that's been championed here at Scripps and with the center is called Forecast Informed Reservoir Operations, or FIRO. And so this is a FIRO concept. It started about 10 years ago, and this is at Lake Mendocino. So Lake Mendocino is up in the Russian River. It's north of Santa Rosa. And so this was water year 2013. And if this is what we call the guide curve for the reservoir. It's a relatively small reservoir, Lake Mendocino, and it's operated by the Corps during flood times, and then by Sonoma Water for water availability and water supply during the drier summer months, spring and summer months. And the water is historically has been operated by water on the ground, and so when it goes above this line, it has to be released. So there's flood control room. So if there's another big storm, the reservoir can capture that flood. And this blue line is the 10-year average, right? So it generally, it goes down into the fall, and then those storms bring it back up, and then comes up, and then goes down in the fall again. What happened in 2013 is there was this big atmospheric river in December that there was a ton of water, and then we went into 2014. We went into, prior to this most recent drought, 3 of the driest years on record, right? And so not knowing that and not being able to use forecast, all this water was released. So the question is, right, could we save some more of this water and have more water as you go into drought? And so this is the concept behind FIRO. 10 years later, right? This is where we are. This was last year, and there's been a lot that's been put into this effort and building relationships between the Corps and Sonoma Water because they have conflicting needs. One needs the flood control space to mitigate flood risk, but other needs the water. And so there were a lot of conversations, a lot of work done, but here's the end result. So last year, this black line is what actually happened, and this red line is what would have happened without this idea of using forecast to manage the water. And because they could see, right, there was this big atmospheric river, And they've agreed to have more flood control space because they know they have a sense of using forecast of whether or not something big is going to happen. And so they can release water ahead of really big storms to help mitigate that flood risk. Or if there are no atmospheric rivers coming or big storms coming, they can hold on to that water. And so last year there was about 13% more. But I would say even more impressively is during this was water year 2020. So if you remember, 2019 was a pretty wet year. And so if you see here, it came into the water year relatively high. And then, it came up to the top of this Firo pool, or this extra space that they would allow the water to go up into because they could see no more atmospheric rivers were coming. And they were able to hold on to this water. Otherwise, they would have had to release it. And so this was almost an 18% increase. And so this just demonstrates that it works in both wet and dry years and overall improves the resiliency both to flood and drought, right? If you can release before a big event, you have more flood control space. But if you can hold on to it when it's dry, it helps mitigate against drought. So you get best of both worlds. This is a very integrated, interdisciplinary, interjurisdictional process. And there's a core steering committee that comes, it's local, state, and federal agencies that are working, it's environmental, it's the local water agency, it's in California, it's Department of Water Resources, it's U.S. Army Corps of Engineers. And so it's the steering committee that sometimes have conflicting views, but all come together because they know that they have this common objective of better resiliency, whatever that means, and how to get there together. And then there's work teams, so scientific technical teams that do the studies that are needed to see how well this would work in individual watersheds. And then there's a larger Firo community. And so I showed you Lake Mendocino, which was the first one, and that's where it started. There's another reservoir downstream, Lake Sonoma, that has been kicked off in the recent years. After Lake Mendocino, we went down to Prado Dam, which is in Santa Ana. And this one's kind of cool. I don't have a figure of it, but one of the things that they do is they hold on to the water if there's no storms coming, and they can use that water to then recharge the groundwater. So they release it much slower, and then they can store it in the ground. Then another one that's recently kicked off is Seven Oaks Dam, which is just upstream of the Santa Ana. And then the first group of dams that we ever looked at was Oroville Dam with New Bullards Bar. And so they're managed, it's a coordinated management, I guess is the best way to say it. It's not, they each have their own management, but they work together to help prevent flooding. And then most recently in the Pacific Northwest is this Howard Hanson Dam on the Green River. So this is where all the Firo pilot studies are going. And the last thing I want to end with is, like I said in the beginning, it's a really great team that I'm fortunate enough here tonight to represent. And this is just a snapshot of all those different people. And whenever, I know Harry said, and it's true, I do very much like the interdisciplinary nature and all the work that I get to do. But whenever anybody asks me about the best part of my job, it's who I get to work with. And it's all these people. So I wanted to make sure I gave them credit. And I will stop there and happily take any questions.
My question actually relates more closely to science communication than science per se, but science communication has social aspects that make it important. So I just wanted to float the idea that the use of the word river is a new metaphorical extension of people's folk literal understandings of river. At the beginning of your talk, you mentioned that the ratio of width to length was the initial rationale for choosing to use river. But as a metaphorical extension, what I'm wondering is people's understanding of rivers is much deeper than just the width to there are slow rivers, fast rivers, and the question is that's what, without further information, people will map their literal understanding of a river onto atmospheric river. My question for you is, how well does the science hold up for advanced mappings of folk models of rivers?
I think it holds up relatively well. And I say that because there are some that move relatively quickly, right? The winds are, when you have stronger winds, they move faster, like a river would move faster. There's some that are shorter. There's still a length to width ratio in terms of detection, but there's some that are a little bit shorter and not as elongated. There's some that are more zonal. So there is a lot of variety in what can be an atmospheric river. So I think it holds up relatively well. It probably isn't a perfect comparison for all the different, and also, rivers versus stream, there, you could go pretty far down that. But I think in the variety of different types of atmospheric rivers to the variety of types of rivers generally, I think it holds up reasonably well.
Hi. You've talked about atmospheric river being sort of a new concept in the public, and I'm sort of wondering how much of this change in our understanding has been, I would say, intellectual understanding versus the increase in our computing power and observational instruments and so on. Is it more that we're getting better at seeing things that we understood before but just didn't have the measurements, or is it that we're getting better at understanding things that we didn't understand before?
I think they kind of go together as part of it. That the CalJet was, I talked about atmospheric rivers, it was more of a field campaign to understand atmospheric rivers, which was in the late 90s. And I think that really helped improve our understanding of kind of what these storms were and atmospheric rivers were. They've always been there, right? It's not a new phenomenon. It's a natural phenomenon that has always existed. But in terms of being over the ocean and not having, I would say, quite the same attention to them as, say, hurricanes or other earlier on, I think there was, I guess the long story short, they went together, right? The observations helped understand what they were. And then with that, there came more modeling too. And so I think it was this kind of Venn diagram of both that really helped move the science along.
In the beginning, you showed a map of the world and the frequency and number of atmospheric rivers all over the world, and I noticed there was a large blob in the Northeast. So are nor'easters also called atmospheric rivers?
So nor'easters often don't have, nor'easters are cyclones, right? They spin, and so I'm going to take a step back. Atmospheric rivers often have a cyclone associated with them, and I don't know if you can kind of imagine this, but like if you have this moisture and you have your cyclone, it kind of spins up the atmospheric river. And so it's not always the case. You can have an atmospheric river without some of the cyclone. On the East Coast, I have to admit, I don't study them as much on the East Coast, but nor'easters are still very much that cyclone. But with the water, it could spin up kind of those atmospheric rivers too. So I think the impact generally in the Northeast is still more for nor'easters, but there can be kind of an atmospheric river feature associated with them.
I'd like to know how artificial intelligence is factoring into your modeling, and how accurate would it be in predicting future atmospheric rivers?
So I think this is a fascinating topic. I will just scratch the surface of it. I mentioned, some of the machine learning. So there's a lot of post-processing. So after the model's been done, using machine learning to improve upon those models to see biases that we wouldn't have been able to see without machine learning. One thing that we're starting to look at, and some of the private companies and computer scientists have done, is we create something called reanalysis. So we think of them as like observed data sets, but we don't have the actual observation. So all the observation goes into a model, and it creates IVT or winds, humidity, temperature all throughout the atmosphere. But it's with a whole bunch of observations of what actually happened, and that's called a reanalysis. It's our best guess of what actually happened without having all those observations. And what machine learning is doing now is using that to then take that and predict the future. And so it's a learning process. It learns on the reanalysis and then uses that to make forecast. And so there's been studies done, and they are as skillful as right now as a lot of the forecasting models. I think there's many, but one of the big questions that are still out there is, because it's based on historical information, how well would it capture something that's not in the historical record? And can it do that? And especially for extremes, that's really important. And so I think that's something that we're still trying to figure out exactly how to do. But I think there is the potential to really change the focus in the weather community on these reanalysis data sets to get those as good as possible to train models, then to use them in the future.